Hi Davide, it's Alexander Sims, student number 10402796, and today I'm going to demonstrate my CUDA application to you. I wanted to build an application which showed the differences between image processing using GPU. I believe I've done so. I've built a Gaussian kernel which runs on both the GPU and the CPU, and then the results are compared from this main frame here. So I'll just show you a little bit of how the code works first before we dive in and take a look at the running application. So first of all, we have our Gaussian CPU method, which basically allocates all the memory that it needs on the CPU, calls this convolution kernel 3 times. The reason why we need this kernel is because to apply the filter, we have to split the image into 3 respective channels, do the filter on them, and then remerge them. And then we have our convolution kernel here, which is called 3 times like I just said. What we do in this is we loop round for the width and the height of the image. Then we get the filter width and the height, which is a stencil method. The stencil is normally a 3x3 grid, sampling 8 neighbouring nodes around a middle node. From there, we clamp onto the bounds, get the pixel like we would in CUDA by doing the index times the columns plus the current offset, and then we get a value of sigma and apply that to the pixel value, and then output that to the new channel value. And then that gets returned, obviously, once it's finished its computation, that gets returned and drawn back as an image. Same principle for the Gaussian. In the GPU, however, we have 1 thread per pixel, so that it speeds it up significantly. Unfortunately, I couldn't find anywhere to use shared memory. I didn't see the benefits. I didn't really understand where I could apply it, so I left it out. We have a separate channels method again. We have a recombining channels method, and we have an allocate to GPU method with some cleanup code here as well. Making use of CUDA device synchronized to ensure that everything's nice and synchronized, and then we write back to this output image, and then in our kernel here we can use that to draw out to the output frame. So now I'm going to show you the actual application in action. What it does is it takes in an input benchmark of frames that you want to process and see the performance difference against. So we'll do a sample of 50 frames here, or 25 frames. You'll notice that the GPU implementation goes very fast, so the cameras will pop up and they'll close almost instantly because it processes the images that fast, whereas the CPU is drastically slower. So you can see here, and now it's switched over to the CPU. It's very, very slow. So we will just watch this through quickly. Admittedly, I probably could have multi-threaded this, but I've been having a lot of problems getting the compiler up and running. So getting it working like this was quite a feat in itself. As you can see here, the GPU is about 31 times faster. Let's go and do that with a smaller subset and see if the benchmark result is about the same. So let's do 5 frames. And again, 29 times faster than the CPU. So the results remain sort of average. Do one more test with just 1 frame. And yeah, about 33 times. And I'll write this all up in the report, obviously. But that's it for my application. If you want to build it on your machine, you're going to need the x64-bit version of compiler. You're going to also need OpenCV version 2.4.10, and finally you need CUDA 6.5. I've built this in Visual Studio 2012 as well, so you're going to need that. Hopefully that's alright, and I will leave the rest in my report. Thanks.